Just 3 seconds. Can you please project completely to this one? Yeah, it's last lady for some of the filters. I wish I hope next come up with as cool as possible. Right now there's 3 travelers Aaron, Kevin, and myself. We have 4 posters for sure, and there would be another spot if no one can get to another, so we can use core spot for the it's absolutely perfect for the slopes. Let's make a quick like run. Here are the printouts. So starting from Aaron, David, and this doesn't have inspired comments. At the time when we will be referring the offers here. So if you spend about 20 minutes per post, it will be reasonable. Posters are good. So, all 5 are here. The plan is to have a very final version by the Wednesday night in 30 hours from now. And send it to John email or to me or to both. We'll probably try to put it again in the public so it will be easier to transport. So the first presentation, first polaron is the Yes, thank you very much.
So in our group, we're primarily focused on photo-induced dynamics and semiconductor materials, and the material that I specifically focus on for most of my projects are lead halide perovskites. And these lead halide perovskites are interesting both for applications and in terms of theoretical modeling, because for applications they've shown to kind of overtake the photovoltaic industry. It's going commercial in roughly about 10 years. So they show very high efficiencies for photovoltaics, and they also show good efficiencies for light emission as well. And in terms of photo-induced processes, one of the ways that people have rationalized their use of photovoltaics is that once they're photo-excited, you have an electron and hole, they interact with the lattice and form polarons. And so, and polarons can be visualized with these couple of images I have in the introduction here. So in this case, this is just a hole, so we remove an electron. And then the hole density are the colored contours. And what happens is once you put the charge in, the lattice is off, so there's a lot of nuclear reorganization. And there's enough to influence or to create like bound states. And those can be visualized with this little diagram here. So these blue lines essentially represent like a Coulomb interaction or a Coulomb potential from the ionic lattice. And it creates a little potential well where the charge carrier goes to the bottom or minimum. And another interesting fact is that since it's a Coulomb potential, the internal states should be analogous to like hydrogenic transitions. And what we primarily focus on in this poster are optical transitions within this little within this potential well, and then non-radiative dynamics within the internal excited states within the potential well. So that's essentially the overview of what I'm going to be presenting. And so the ultimate goal is to model both electron and hole simultaneously as polarons, but we decided to take baby steps towards that. So we first just do a negative polaron by injecting a charge, or just a positive polaron by removing a charge from our model, and looking at the observables we want with those first before going head first into simultaneous positive and negative. So essentially the flow chart for how we conduct our work is, so for each model there's an equilibrium number of charges, and then we modify that by adding or removing charges. So if we remove a charge, that creates positive polaron, add charge creates a negative polaron. So we change the charge, throw it into DFT, get the reorganization of nuclei, and then we characterize the change in nuclear positions and that effect on the optical spectra and the non-radiative dynamics of material. And in terms of talking about the dynamics, there are two potential ways that you could think about them. So you put the charge in, and one opposite extreme is that the lattice instantly reorganizes faster than that energy can dissipate. So in that case, you'd have a hot polaron. So we would have, our charge would be stuck in the top of the potential well, or you have the opposite effect where you put the charge in, it gets rid of all this energy, and then the nuclei reorganize, and that would be a cold polaron. So that would be this charge stuck in the bottom well. And so the way that we set up our dynamics is we are simulating hot polarons so that we can look at radiative and non-radiative transitions of the excited state. And from there, so our methods, some technical details about how we did our calculations. The most pressing thing is that for material consideration is that we deal with lead orbitals, lead p orbitals, and those have high angular momentum. So we have to include spin orbit coupling into the calculation. And then that took some work to extend that to our non-radiative dynamics. So that's kind of one of the methodological novelties of this work. And so essentially the main interaction that we have to deal with in describing polarons is electron-phonon interactions. So from this fancy second quantization description, you can break it into two types of terms. So you can deal with organic, or dealing with the same indice terms. So that essentially describes nuclear reorganization, or just movement along the potential energy surface. And so that would be essentially how we do our geometry optimization. Then you have these transitions between different bands, and those are described by non-adiabatic terms, and then that's how we describe the dynamics. And so that's methodology out of the way. And so to look at structural characteristics of the polarons, we computed radial distribution functions for each system, so for the positive and the negative. And in this, we only look at the coordination between lead and bromine. That's illustrated with this picture here. So A is a lead to bromine bond distance, where B is a bromine to bromine coordination distance, which is across the lattice. And for both models, we see specific characteristic nuclear organization. So for the positives, we see that there's really no change in the lead-bromine bond, but the bromine-bromine coordinations are increased. And so that indicates that these octahedra, there's no change in elongation, but they kind of rotate so that bromines are interacting more. Whereas with the negative polaron, we don't see a change in the bromine-bromine coordination, but we see a change in the bond distances themselves, and we see a little bit of an elongation of those bonds. And we just rationalize that due to, if you consider when you add a charge, they're mostly localized on lead orbitals. So lead is 2+ in the lattice, so when you add a charge, it becomes slightly less positive. So its oxidation number reduces, so it gets reduced by a fractional amount. And the bonding in these are partially ionic, so there's less ionic strength to restrict the weight a little bit further. So that's how we rationalize structural characteristics. So we do see signatures of what we can attribute to polaron formation, which is a good sign. So we're looking at the geometry. We look at optical spectra within the polaron well for both positive and negative polarons, and looking at, so we also screen for multiplicity of the polaron as well. So we have singlet, doublet, and triplets for both models. And so these represent the density of states. So blank space represents the whole occupation, whereas shaded region represents the added electron occupations. And I put a script for that spectra. And so we compute spectra for both these models. We essentially see the same trend, is that the singlet and the doublets are generally brighter and have roughly the same transition energies compared to the doublets for both positive and the negative polaron. So that's the main takeaway we took away from out of the spectra is that singlets and triplets are generally brighter. So we focus more on those for the dynamics in the next section. And just as a methodological comparison, we chose one of the models and screened between functional choices because one of the things with polarons is that they're characterized by self-trapping of the charge, so there's known issues with the functional of PbTe of the charge delocalizing too much. So just to check that, we screen electronic structure and spectra for the negative singlet, and in our, so you can see that the density states are roughly the same. The peak positions are the same. There's a little bit of changing in the intensities. And we look at the spectra. So the green is the PbTe functional, and the black is the HSE. So you can see similar characteristics that are just offset by energies, whereas the HSE has a higher transition energy, which is what you would expect, because HSE generally underestimates, or PbTe underestimates gaps. So we see the same signatures, so the trends should be qualitatively the same. So moving on to dynamics. And so to describe dynamics, you have to be able, so non-radiative dynamics, you have to be able to couple electronic and nuclear degrees of freedom. So how we implement that is we run ab initio molecular dynamics for our models, and then we track the fluctuations of energy bands over time. And from these fluctuations, you can compute non-adiabatic couplings along the trajectory, and then post-processing of the couplings, we can get state-to-state transition rates for our models. And so top row is specifically the negative polaron singlet, and then this row is the positive polaron singlet. And just looking at these red field tensors, which we describe the rates of transition, the main features, just comparing these two, we can see that the negative polaron has lower intensity rates compared to the positive, and there's less spreading along the diagonals. So that indicates that the positive polaron, there's more non-radiative transitions possible. So it should show quicker non-radiative cooling compared to the negative polaron. And then when we run the dynamics for our systems, we do see that. So this figure here is log time versus energy for our states. And so we just choose an initial condition and then run the dynamics based on the rates that we calculate. And we can see that the negative polaron does cool, or does have a longer hot carrier lifetime compared to the positive. So the positive cools roughly around a picosecond, or shorter than a picosecond, whereas the hot polaron shows about 10 picoseconds relaxation. And then screening just for different initial conditions. We computed the rates and then plotted energy dissipated versus block time for these transitions. And essentially what we see is that if we compare the polaron cooling rates to models that we don't consider the polaron, so it's analogous to free charge, we see that the polaron models have a longer lifetime compared to the free carriers. So that indicates that there is polaron formation, or signatures of polaron formation in our models, in our methodology, because you would expect that the polarons are generally described as screen phonon interactions, so they should reduce non-radiative transitions compared to free carriers. So that's a good sign from our cooling rates. So this describes non-radiative relaxation of excited polaron states. And then along the same trajectories, we can compute radiative relaxations. So essentially, we're trying to characterize the photoluminescence capability of the polaron to see if it could be, to see how efficient it could potentially be at emitting IR photons. So these plots, same log time, and then these give the energy of transitions along the trajectory. And then, so the colors just represent intensity. So once carrier cools, it gives photoluminescence from the lowest energy transition. And then just from this plot, we can see that the negative polaron has about an order of magnitude more intensity for emitting photoluminescence during its trajectory. But to better characterize how efficient it is at emitting, we calculate a theoretical photoluminescence quantum yield from our radiative and non-radiative rates. So we take the non-radiative rate to be approximately the lowest energy recombination from our Redfield tensors, and then the radiative rate is we compute from Einstein coefficients for spontaneous emission. And we just plug those into a simple quantum yield equation for rate of radiative over all the other recombination pathways for the system. And then when we compute the quantum yields for systems that we investigated, we see that generally that they're very low quantum yields. So the most efficient emitter was on an order of 10 to the negative fourth efficiency. So not very efficient. So that's like a 0.01% quantum yield. But so it's not very good at emission, but we did notice an interesting feature that between all of the models that we investigated, that there was like a range of different photoluminescence quantum yields. And looking into the data more, we see that for all the models, the radiative rates are roughly the same, to differ by maybe half an order of magnitude, while as the non-radiative rates for our efficient emitter, and show 2 orders of magnitude reduced recombination rate. And so to try to be able to look in to see if there's a possible mechanism for why we observed this trend, we decided to try to hunt for resonances between vibrational modes of the system and transition energies from the system. So that's what this plot is describing here. So essentially we're looking for frequencies of vibration from normal mode analysis and how it compares to optical energy transitions from my IR spectra. And we see, and this is negative polaron, positive polaron. And we do see from aligning the axes, there appear to be some resonances between vibrational modes and the IR spectra. So we see for our most efficient emitter, which is the negative singlet, there appears to be in resonance with this ammonia feed, whereas the triplet is in resonance with the mode from the carboxylate ligand on the surface. And then the positive polaron is in resonance with lower energy vibration from the lattice. And so the main distinction that I see is for our negative polaron. There's a 2 order of magnitude difference between these 2 transitions. And the way I rationalize what the difference was is that for the carboxylates, they chemically bond to the system, so they provide active modes of vibration, which directly contribute to the non-adiabatic couplings. Whereas for these NH bending modes from the ammonia, they don't provide electronic density to the surface. They're more of spectator modes, and so it doesn't actually provide any vibrational pathways to release energy. So that this excited state has a longer lifetime due to a detuning from other vibrational modes. So yeah, that's how we explain the trend that we observed from our recombination rates. And so that wraps up the story of having individual polarons in the models. And the main takeaway is we do see consistent signatures of polaron formation due to either bond elongations or coordinations occurring between halides. And the main takeaway is that it is possible that these polarons do have spectral features from transition to the eternal excited states. And they are pretty bright, but when you try to look to see if they could be possible photoluminescence materials or potential IR emitters, that they're generally quenched by higher energy vibrational modes from the surface ligands on these models. So it's just an instance of the surface providing, it makes the system stable, but it also helps induce non-radiative transitions in the system. So the importance of surface chemistry on photophysics of the polarons. And then, so that's all one paper in itself that was published in JPCC earlier this year. And then we're moving on to the system that we're mostly interested in, is the simultaneous positive negative polarons in these models. And so just to give an idea of why simultaneous would be different just compared to having an individual charge, if you look at the same plot that I described earlier about the charge density in the model. So previously it's just a whole charge evenly distributed throughout the whole crystal. Whereas if you put both the charges in at the same time, it's like you have positive and negative, so it's like what charge is going to win out in the model. And then just plotting charge density, putting in a hole and an electron. So the hole is the yellow color, the yellow density, whereas the electron density is the blue. So we see in this model that when we introduce simultaneous charges with that, it's kind of like shells of charge. So at the very interior, it's negative. And so the next layer out, it's kind of a positive charge. And then it's another shell of negative charge. So you should see quantitative differences in nuclear organization and excited state dynamics as well. And so just for this model, so looking at radial distribution functions again. So it's the same A and B peaks as described above. Whereas before, we just had one of the charges in the box, we would only see one of the peaks move significantly. Whereas if we put both charges in, we see reorganization of both A and the B peak. So I guess you would kind of expect that too, because they provide equal contribution. Like you'd see one only changes A, one only changes B. So if you put in both, we see changes. But the interesting thing for simultaneous is that if you just put in a negative charge, the bond would elongate. Whereas for this model, when we put in both positive and negative, the bond contraction. So it does show a difference in the bonding of the system when you have both charges. And so, and for electronic structures, again, we screen for different spin multiplicities, so singlet and triplet. And in these density states figures, the hole is represented by this white space in the density states, whereas the negative is represented by the filled red area in these curves. So for the whole polarons, for singlet and triplet, the density of states looks qualitatively the same. There's not a lot of changes in the peak positions. Whereas if you look at the triplet, though, there is kind of a broadening of the density of states in the conduction band. And so we do see the signature of this broadening show up in the IR spectra for this model. So computing IR spectra for the model, we see that for the positive, so the black solid lines, those are roughly show the same characteristics in terms of energy and where the peaks are located. Whereas with the negative polaron, you see that the lowest transition energy is 0 eV. Whereas for the triplet, we see a bright signature at a higher energy for the same model. So the way that I kind of think about that is for the triplets, it introduces another interaction that can split the energy bands to provide the broadening. So it's well, triplets are magnetic, so it's magnetic force, which kind of rearranges the density of states. It opens it up a little bit. So that's how I characterize or understand these transitions. Then you can also look at across the band gap transitions, which I don't have plotted here. All right, and let's characterize two intensity yet. Further work, or further goals for this work is to try to see if we can characterize the influence of polaron degrees of freedom on the radiative recombination in these materials, because it is kind of counterintuitive that if you have two polarons, you wouldn't expect them to be bright emitters, because they provide a barrier to recombination. So these materials, they do show experimentally efficient emission. So it is kind of counterintuitive. So it is a fun little system to try to characterize and figure out. And that's the presentation.
Okay, that's an any suggestions or any critical points, or if you want just to glorify and say how nice it is, you can skip. There are some questions, please.
So, I guess first question is, what's the meaning of large? What's the meaning of large?
So large is defined, so you can have two different limits. So you can have a small polaron, where it's a charge trapped on a single atomic site, like a transition metal, for instance. Whereas a large polaron is just, it's more delocalized over multiple unit cells. So it can have a variable spatial size depending on the type of material. And by size, it's like order of 10 nanometers.
And also, I guess we use SQE notation.
Mm-hmm.
It's just on the analog function in the output.
Mm-hmm. Yeah, analogous to like atomic transition, or symmetry of the envelope function.
And the IR emission. Did you try to compute the IR emission of the neutron model?
We use.
Yes. Modeling if there is any intraband IR emission from this one. So how strong?
I get what you're saying. I mean, it would be weak compared to everything else, because so it is possible to have IR emission with a hot electron from the neutral model. But I don't remember those. They didn't have a lot of intensity, or they were a lot less intense than the main photoluminescence. But I guess not well shown with this figure, but these, like the energies of transitions, do correspond to like these transitions.
More questions or suggestions? If no, let's think Aaron once again. And Aaron, please collect feedback. I have some, and if you are writing, just disassemble so that you can submit those. My suggestion is estimate for hours because your two-dimensional electron hole orbitals seem to use different colors for here and there. Like your electron is blue and hole is here and here. Otherwise, I don't care, but some visitors can be confused. And also, it's cosmetics. If you label a singlet with bright green filling, you may use the same color. David, would you like to share something about your project?
So what I'm looking at in this project is the photo optical properties of two-dimensional perovskites. And when I describe two-dimensional perovskite, what we're looking at is a perovskite layer that's been separated by some spacer molecular atom, causing the perovskite to form a sheet instead of a bulk three-dimensional model. And I'm looking at two different types of spacers here. One of them is a organic spacer ligand, and the other is a inorganic ion. So the reason that these have been looked at is the perovskites have good properties for photovoltaics, but the bulk perovskite materials degrade easily to environmental factors. Where we see that these two-dimensional materials have a greater stability compared to their two-dimensional models.
If you are not sure how to logically arrange the main outcome of your calculations are rates of relaxation rates. And you may arrange everything you talk about targeted to this. Like pretend that your goal is to find relaxation rates, even if it is not. Pretend that the main achievement that will save the world is to find relaxation rates. Like try to connect it and then arrange methods, everything in this direction.
So what I'm trying to determine with these calculations is relaxation rates, because a longer relaxation rate allows for a greater chance for the charges to separate, which is essential for photovoltaic processes.
So which methods are needed to fulfill this goal?
So to determine the relaxation rate, the rates, we want to use the final equation that I have listed here, the one that I apparently didn't make big.
No, this size is perfect. Visitor the poster will see. Would you like to briefly guide us through equations?
So my methods I have. We're looking at the as we look at the results, we see that the density of states is determined by factoring in the occupation.
Can you conclude it?
Yeah.
I do not want to doubt that you can explain each equation, but what is the logic? It's not like examiners show, look at me how many equations I need. Your goal is to get relaxation rates.
Yes.
And the equation for relaxation rate is missing. It should be the last one after your equation for expectation value of energy. And we are doing this collective editing and collective presentations with the purpose that we can borrow ideas, maybe not literally copy paste, but just borrow the ideas of these equations and look for trying to find an equation for relaxation rate in other posters and copy it to your poster. A little suggestion: if anyone is writing feedback, you may focus on it if you agree. The methods could be hard for a single human to navigate through at once, and they can be divided and cut. So there are at least three categories. So one can split equations in three pieces. First, and if you are listening what Aaron was doing, it's quite standard. First, static programs. Second, dynamic processes. And third, observables. Like observables is basically your rates. But it's your free choice to make this categorization something different, but chopping it on categories will help logical jump from equation to equation. Please keep going. And you're very welcome to think aloud, even if you're not sure which thought is the best, share them out. What to do here? Might be the time to depart. I did so nice red-filled figure in the middle of the column and no one focused on it. I should probably bring everyone's attention. So where are the rates of relaxation on your green figure? Can you visually show it?
So we have some rates, little hearts.
Okay, and you give quite precise numbers with like 2 significant figures.
Yes.
How do you get them? Do not tell the code, give them. Tell how they compute it.
It's based on the average energy at a specific time. Compared to the original energy at time 0.
So, is there a fitting procedure involved?
Yes.
So, fitting to each function. And feel free to ask the audience.
Coupling?
No, which mathematical function?
Oh.
So your energy of electron decreases with time.
Yes.
How quick? According to which word? Does it decrease as minus t linear or 1 over t?
If I remember, it's 1 over t, but I'm not.
1 over t is a good approximation, and most typically is assumed that it is decreases exponentially. So what you are doing, you are fitting this dashed line to exponential function, finding the way. Okay, what are the conclusions?
We see that as expected, the larger layers of perovskite have a smaller band gap compared to the smaller layers of perovskite. We also see that the fully inorganic model has a faster relaxation rate than the hybrid models.
Done? Okay, let's thank David. And any suggestions to express them verbally? Any questions or thoughts? What what is recommended to focus. Primary process.
Is your inorganic layer or inorganic system that N equals 4?
Yes.
So I mean, if you don't know what to talk about, that would be an easy comparison. Like just point out differences in their spectra and density of states. And then all the other observables as well.
And yeah, I noticed a problem with my couplings yesterday.
Mm-hmm.
So I'm fixing them, and I'll have the figures for that.
Very good, very good. More suggestions? If not now, then let's thank David once again. And please collect the feedback and try your best to read and implement.
Okay, so basically in this study, we focus on our solar cell composed of perovskite and also a titanium cluster and organic dye. So the titanium cluster is electron transport material. The dye is a cold transport material. So basically, we apply electrical field normal to the surface of the perovskite. And then we study the induced electronic structure of our models. We then characterize the charge carrier dynamics of this system under different electrical fields. So basically, for semiconductors, we shine light. So there will be hot electrons and hot holes. And this hot electron, hot holes will just relax to the ground state through lattice vibrations to basically just characterize these processes. So this is a PfT study for the ground state structures. We do our calculations in LAS using PbTe function. This is still restricted PfT. And for the charge carrier dynamics, we have cone made scripts, so they are equations. So here is my mathematical structures. This is 0.5 electrovolts per angstrom per system. From top to bottom, the electron field just equals. And we can see from top to bottom, the band gap increase from 2 electrons to 1.2. This is the relationship between band gap and electron field. So basically, we have a linear relationship.
So can you please verbalize this positive electric field? How does bottom of the titanium dioxide band changes?
Okay, so just as the pedals have 3 components: perovskite, titanium, and organic dye. So if we change the electron field, so basically the band of perovskite stays the same, but the band of the titanium just shifts to the right.
Which means increases.
Right.
With positive electric field, it moves up.
There's a decrease of the electric field.
So with negative electric field, it moves up.
Right. And the organic dye just shifts to the opposite direction. Shifts to the left.
And I apologize for asking silly questions, but now, how does the maximum of the valence band or HOMO of the die behaves with the same negative field? HOMO, how does energy of the HOMO of the die changes if electric field is negative?
Shift left.
Shift to the left, so it decreases.
Yes.
Okay. Okay, yeah, thank you.
So there is a calculated local spectrum. I guess there is some very small, teeny tiny feature around certain levels. Like I believe this is related to the conductivity. So here is a numbers in the log scale. So you can see it is not
So, as electric field goes from positive to negative, the conductivity decreases.
Yes.
And if we go if it goes from negative to positive, conductivity increases by several other magnitudes.
Right.
So change of electric field from negative to positive increases conductivity. Okay.
Yes, here I can show some contours.
Are they for zero? I apologize for interrupting. Are they for zero field or for certain field? Okay.
Shows clearly for the HOMO method density, just focus on the end line of the window. And then we focus on the actually HOMO -7 kilopascal. This is one of the strongest performance. Later we use this performance to look for structural dynamics.
So optical excitation promotes most probable transitions from HOMO -7 to LUMO +7.
Yes.
And what's the frequency for
2.8 to 12 decibels.
2.8 volts and in nanometers? It's like 400 or more precise. Huh?
450 meters.
And which color is this? Is it blue? Okay.
And here we can show the character dynamics from different materials. So, red is just a graphene, blue is a gold, green is there is no change. The left side is character dynamics function, as a function of the energy of time, and white is character dynamics as a function of distance and time.
Before we go further, can we look at the equations? And I do not know the answer. It's not like testing. I'm constructively trying to find. If we do not have any software and we want to write it from scratch, how would we add the electric field into this Pon-Sham equation?
I think it's just like the scale will happen, you just like add on equation.
Can we just put inside these brackets after, yes, like minus dipole operator times electric field. And then even if it is not what we personally doing, it will bring a little certainty.
Yes.
Okay. And then one can add additional rubric into the equations and place the called perturbation theory and tell that energy of orbital I under field is approximately equal to energy of the same orbital without field minus matrix element times electric field. Okay, yeah. It will, just knowing the audience, it will help them a lot to understand what is being done.
Mm-hmm. Okay.
Yeah. And I made this.
Here is a table to summarize its top three transitions for its computer mechanics. So interestingly, they do have a tree. So there's a difference between that two, and you can see the rate of the whole has a decrease. And for the electron, the rate first decrease. Here it's just increase a little bit. So for the point for minus 0.1, it's the rate increase a little bit. This is we have a larger subgap along the trajectory.
Is it possible to summarize this table in a graphical form? Like with x-axis as electric field, and y as a rate, and have different symbols or different colors for different transition.
Another reason minus electric field became a little bit strange is compared to the top three, the band of perovskite also shifts a little bit. So for example, if you look at the field, band of perovskite almost kept the same, but right here it's just shift to right a little bit. Is the way identified there is a linear relationship between that and also an I that externally as a field. It also has some effects on the rate of relaxation.
Okay, but thank you. So, any questions or comments or suggestions? And questions can be not necessarily for improving poster, but if something was not clear and you want to implement the same approach to your suggestion. If I know nothing about it and approach the process for the first time, I'm missing very much a schematic diagram. Some abstract. For example, it could be it's too simple. We do not need it to show that. So conduction then for the perovskite in the side and right, and then one can also show that this folding promotes, it creates excitation, and then electron goes one side, hole goes other side, and then the things that we were discussing, how much the bend edges are affected by field. This conduction band of the ring oxide increases, valence band of the decreases, and it is major, because it is expected that it is a major factor.
This is
More questions and suggestions?
What did you say the difference was when you put in a negative electric field compared to the positive? In terms of density of states?
So I guess one changes we have a larger subfield during the transition. The second is the band of perovskite also shift compared to the other field. And then remember, I guess last time actually I have 5 data points. The fixed data point is at minus 0.3 microvolts times 1. And we can clearly see where is that shape of band structures in the perovskite, which also makes the fixed data point as well.
Yeah, I'm just trying to think. Because it would be, that spot's usually occupied by a halide. So you have some halide. So the bromine P orbital. I guess it's, I'm just trying to think why negative field would have fit, whereas positive doesn't. Unless it's some feature like positive field pushes it deeper into the valence band, where the negative field draws it out into the band gap area. I don't have a direct question. I was just clarifying.
Yeah, I guess maybe I can just double check on the first. So take the first look at the bottom perovskite block making.
More questions or suggestions? If not, thank you once again. Just collect the if it's my floor is yours.
So as I said, during last week talk that we are interested in magnetic field driven with nanowires and graphene. Here we can see the band structure of graphene. Here this one is a balloon zone, and this acceleration. Since the dimension and conduction and evolved, not much, but very good. It's a graphene is semi-good, and energy band structure is linear at these corners, which are called bullet points. Since energy dispersion is linear here, so the dynamic and graphene has an extra I'm going to leave this part. Yeah, so each graphene atom has three nearest neighbor carbon. Each carbon atom has three nearest neighbor carbon atoms, and other yet nearest neighbor atoms. And this is the adjoining Hamiltonian of the graphene. This first term for nearest neighbor carbon atoms, and this second term for next nearest neighbor carbon atoms. If we consider only nearest neighbor carbon atoms and solve it, we can get this energy dispersion relation. And here we have two signs, positive and negative. Positive for conduction band for electron, and negative for hole in valence band. Here these two equations for the eigenfunction of this Hamiltonian. Here obviously in 2 dimensions, and the momentum K is function of K, X, and K, Y. The equation for 2-dimensional wave ticket is here. I didn't edit this question though. So there should be one more term that's a function of Y. And if we calculate the Fourier transform of this position eigenfunction in position space, we get eigenfunction in momentum space.
Can I intervene and
Sure.
correct and suggest?
Sure.
It's not eigenfunction. There is initial condition for solving time-dependent general equation.
Initial conditions.
Yes. And let me suggest some changes right away, which you can accept or could decline. would you accept it? So the logic is after doing reporting the trivial things that can be taken from literature, up here, one uses this information to formulate it in the genome. Then one introduces the magnetic field and solves first time independent Schrödinger equation, then time dependent Schrödinger equation. And for solving time dependent Schrödinger equation, one needs to formulate initial condition. But please think if you accept it and describe
I
it
don't
with.
understand how they are initial conditions.
Yes,
They are what function?
the word eigen should be removed. This Gaussian wave function cannot be an eigenstate. It's guaranteed that it will not be an eigenstate.
Initial conditions mean the wave functions and the initial point.
At the initial time step.
Okay.
Okay, now please explain it by your own words, if you accept this logic.
And then in the absence of external magnetic field, Hamiltonian is here. This is for EF. And in the presence of magnetic field, there is another term here, Hamiltonian. There's the dot product of angular momentum and applied magnetic field. So magnetic field is applied along the z direction, and angular momentum is also in direction. In position space, angular momentum term is here, and the moment space is this one. Now, when the magnetic field is applied, then the corresponding Schrödinger equation here, this one. And since we are considering z directionally, we can consider this angular momentum in the z direction. And this equation is a time-dependent Schrödinger equation, and we can take the time evolution need to operate all this time-dependent Schrödinger equation. And then these are the initial conditions. Right?
Good.
Okay. Here I calculated these are the magnetic electron dynamics when the magnetic field is applied to the graphene. These three figures and three different time steps. This one for 0.12 femtoseconds, 12 femtoseconds, and 24 femtoseconds. And this, the value of magnetic field is here, 0.7 Tesla. And this one for a little higher applied magnetic field, 1.92 Tesla, and the time steps are the same time steps. So here in the when magnetic field, value of magnetic field is lower, you can see there is not much electrodynamics. It starts here a little bit and then a little higher here. But if the magnetic field, the value of magnetic field is higher, you can see more. And these are the corresponding.
May I interrupt?
Yep.
Can you please explain why the figures are hexagonal?
Because this is, we consider this brilliant zone here. So that's why there. And each corner here represents by this red dot, the digit points.
What happens if wave packet bumps into the wall of this hexagon? Not in calculations, but in nature.
It will go to the next one because it just shows the one brilliant zone. It's continuous in two dimension.
Okay. Would it just go into the next band, like rho plus 1?
I'm sure.
Because if, when we draw band structure
Mm-hmm.
in one dimension,
Mm-hmm.
we never get bigger than like pi over 8. It's maximal wavelength. And if you continuously approach the edge, if you need to go higher, the band just flips.
Actually, I'm not sure about if the magnetic field is applied, then electron is excited or not. Because when magnetic field is applied, electron gets motion, but I'm not sure if it is like the higher states.
Okay.
But if you shine light on it, definitely it will. But the magnetic field, I'm not sure.
Okay.
Since it moves in two dimensions, cyclotron motion.
Okay. And you are going to explain the top panel with eigenstates?
Yeah.
And before you go there, I will just close which question I would like, which I'm already writing.
Okay.
Would it be reasonable and would it be possible to present eigenstates in the same format as we present dynamics, to enclose it into the hexagonals?
Yeah, I can do that, but I have concern here because this is for magnetic 0.7 Tesla. Here we can see that the electron dynamics not much spread here, spreading, but here we can see the eigenstates.
What's wrong? Why it is a concern? If you look for dynamics for a longer time, it will spread further and further.
Okay. But here time.
There is no
Not
time
time,
for
yeah.
eigenstate. There is no time.
So for this magnetic field, it will spread like further. I don't think it can come here.
If you
Is it possible? I don't.
If
think
you
so.
wait long enough, if you increase time step or use more steps, there is a high chance that you will go there. The 24 femtoseconds is very short time.
Yes, very short term, but we need short term. We are not interested in like bigger time scale.
Why?
Because in whatever you think, like optoelectronic or photovoltaics or quantum information, they are very quick, like femtosecond or picosecond time scale. It's
But
not like
Why?
electron motion is very fast.
But-
It's not like
No. Aaron may answer it. Maybe we were discussing it. It relates with your very new projects and your very new abstract. So why it makes sense to explore electron dynamics only on short times? Why on the long time it is not as interesting? What happens? Why we are using here Schrödinger equation instead of Liouville, instead of Redfield dynamics? I understand that just because we do not have the codes are not updated, but what is the motivation and justification? In which case Schrödinger equation is applicable?
because here there is perturbation, magnetic field.
Where is relaxation due to phonons?
What is that?
Where is relaxation due to phonons, due to interaction with lattice vibrations?
I don't understand the question. Where
Why these equations do not include interaction between electronic and nuclear degrees of freedom? Why there is no Redfield tensor? Why there is no relaxation? Is it justified?
Yes,
Why?
because it's magnetic field,
Mm-mm.
not like
Mm-mm.
So if there is no heat here, there is no applied heat. There is the system as a like model is not heating.
But there is. It means that you are approximated to zero temperature, 0 K, right?
0 K room temperature.
No, at room temperature. there is interaction with lattice vibrations. And in any experiment, relaxation does happen, does occur. One is focusing on a very short time. The justification is that we can neglect relaxation if you look on such short times that they are shorter than relaxation. So nothing will relax yet. And I'm not arguing and adding argument to support your idea. So one is looking on short times because we want to explore the regime where the relaxation didn't happen yet. Okay, so what about eigenstates?
Yeah, and for this one, even this looks like electron dynamics is not it confined in this region, but here the states look spreading over the free area.
Let's separate this discussion into two categories logically. You are trying to do two things at once, and I'm suggesting to split these two things. So first thing is to just present and describe how eigenstates look like, and second thing, to establish correlation between features of eigenstates and features of electron dynamics. Let's postpone analysis of this connection between eigenstates and dynamics for next 10 minutes and focus only on eigenstates. So can you just briefly tell what they are and what are their features?
So these are the electronic states. This is the state PbTe, and energy is 0.43.
So
I'm not sure.
here's the eigenstates which must be prefixed, right? It's a superposition of several eigenstates to compose the repackaged one. How many eigenstates do you have?
I've got the question. I have the answer. I need a few seconds to prepare. Can I?
Yeah.
answer the question? I will do this. I will quickly write and then comment. both feasible boxes? Okay, so there are two ways to propagate wave function in time. So suppose that our goal is to start this wave function at time 0 and obtain wave function at time bigger than 0. So one way is to apply evolution operator that includes Hamiltonian explicitly. And in this case, we do not care about eigenstates at all. This is very universal but very numerically expensive. Your question relates to more inexpensive way which we do not apply here. So this results by Fatima are done with time evolution, which is applicable even if one cannot find eigenstates or if they have no sense. Like if there is, if it is like plane waves, strange things are more traditional instead, and these all solutions mean solving time-dependent Schrödinger equations. As all things are solution of time-dependent Schrödinger equation. And more canonical traditional way is to first solve time independent, find set of eigenstates, and then construct time-dependent solution as a superposition of eigenstates, each of which evolves in time according to its eigenenergy, and this solution enters in the partial solution, enters into the general solution, enters into the partial with weight coefficients. And these weight coefficients are obtained by overlap between initial state, time equals 0, and certain eigenstate. So if we would implement, if we first use eigenfunctions, eigenstates that Fatima has already found, and then solve it according to this equation, the code which currently runs for an hour, this would run within like 1 second. Your question about number of in which range this I changes. Number of the eigenstates is equivalent to number of grid points. So it's two-dimensional grid, about 60 by 60 by 50 by 50. So about 250, 2,400, 3,000 grid points. Number of eigenstates is the same. But in order to construct legitimate solutions that you describe physics and we seem to get, it is more than enough to use like first 300 eigenstates. The eigenstate with higher energy can be thrown outside in a similar way as designers of class do. They are setting up the n-hat parameter and do not consider plane waves which give energy more than 500 volts, but they definitely will not contribute in physics. Does that answer your question?
So then are you looking for features from the time evolution, or similar features between eigenstates and the time evolution? Or trying to hope to see that some characteristics appear?
Is time evolution of electron wave ticket from one people into another?
But it's not all. But we,
I guess the question is like whether you can get to the same point using the two different methods, or ideally that's what you'd like.
there is no doubt that both methods will give the same result. The idea to find eigenstates came much later than original code. It's like addition fast equal to it. Would you like to add more about Aaron's question about connection between eigenstates and dynamics?
Even I'm not clear.
Okay, let me add.
I have a question. I will ask.
Okay, so after looking at your data, I thought you have very clear verbal explanations because you place the data in a very logical way. So here are sets of sample eigenstates. So although there is like 60,000 and it's interesting to use maybe first 300, 400, pretty much shows representative, like 171, 2, 3. And the same numbers are explored at different values of magnetic field. Okay. And the energies of this state with the same index are not drastically different. They're in the same range. But the shape of the wave functions is different. With a larger value of magnetic field, the eigenstates become more delocalized. So here it is approximately 2 peaks. Here it comes with a ring with certain peaks with maximum and certain peaks. Which means the eigenstate corresponds to delocalized wave function. And localization here is not in position space, it is in momentum space. So this circle means that if we are in this eigenstate with this energy, there are several values of momentum which are allowed simultaneously. Probably in the Cartesian space, this ring will correspond, this state will correspond to the fact that rapidly moving in all directions. While here, this 2 peaks means it moves only in 2 directions. So it's 2 peaks and a certain value of momentum means it is a plane wave index. To the power I index.
In that case, it could be plus or minus.
Yes,
But in that case,
for the like if this is x, then for x it goes one part of the wave packet goes positive and another negative, and for y both of them are going in the same direction. If one would use magnetic field equals 0, all eigenstates will be represented only by single delta function. Plane wave will be eigenstate of this field. So as far as one, this trend maintains larger field, more delocalized eigenstate. If one assumes that this trend, so this was part 1, now this of eigenstate. Now, if one tries to establish connection between features of eigenstates and features of dynamics, and it is really great that everyone placed these same values. So it's like a logical connection. So for bases with more delocalization, it is expected that departure from initial localized person wave packet will happen quicker on a further distance. So it brings on a smaller distance and goes further. Here it looks like brings on a couple of sub peaks and goes not too far. Here there are more smaller peaks and they are more the further distance. If it will be classical unit, non-quantum mechanics, but just classical particle, then in magnetic field, the initial momentum of electron will just go into circular orbit. Since it is quantized feature, the eigenstates do not they do not prefer one or another direction. It's more like they tend to form the circular patterns. Therefore, instead of going one preferred direction, prompted by environment, it distributes almost equally in both directions. And it is a major surprise by comparing this results with intuitive expectations based on classical.
So is there any physical meaning of the labeling of the states, like state 171. Of course, previously you said maybe just the first 300 and state matters. So state 1 is the most important one.
Be the most bound. Oh, I guess it depends on. I would assume like state 1.
We have time for, oh yes, we have a little time. Let me bring up all eigenstates. And whoever of us, I don't know if Kevin, but if you guys are new or Aaron showing this poster, so probably you will paste, you will put the iPad is moving nearby.
One thing is not clear to me is that if magnetic field is applied to electron, it's going to higher state. If electron does not go to higher state, why we care about this 251 state with higher state?
Yun, can you address this question? Please discuss with Yun this question, and I will try to bring up a movie. I just need a couple of seconds, but ask him once again. He should be able. Just repeat the question.
So do you have the answer why we apply magnetic field and if electron is not going to higher state, why we apply light on? So when magnetic field is applied, does electron go to excited state? I know if we apply light, then it goes, electron goes higher state. But in magnetic field, circular motion, yeah, PGM. It's on the ground state. That's my confusion. Like electron is going to higher state, or it's on ground state and moving.
If electron is in ground state, it cannot move. It's the equations that I was showing you have them. The motion is constructive and destructive interference of multiple eigenstates. And in order to represent motion in the best way, one would need to include as much as possible basis states. If one truncate basis to lower energies, the precision will suffer. So taking more and more, and all eigenstates will increase precision. And here are the eigenstates. It's maybe not best presentation, but you see in the lower part there is an index of state, and in the upper part there is an energy. So when the index of state is close to 1, they are more localized and in the K prime point, in the Dirac points, right? But as far as energy increases, they start to be constructed of all Dirac points contributing simultaneously, and instead of points or little spots, they take shapes which look more like a circle or rectangular or some closed trajectory. And these eigenstates that represent closed trajectory would contribute to circular motion or motion along trajectories. More questions? If not, thank her once again. And now the floor is given to Kevin.
I'm pulling up my notes on my cell phone.
Yes. Oh, yes, absolutely.
All right. So before I get into the meat of the talk, I just want to quickly introduce non-adiabatic dynamics and specifically doping. So first, non-adiabatic dynamics. In the regular adiabatic approach, when an electron is transitioning between orbitals, the nucleus is assumed to be still and not moving. So if we look at this equation right here, the expectation values are going to be 0 because the orbitals aren't changing with time. However, in the non-adiabatic approach, the nucleus is moving, or is vibrating. So therefore, the orbitals are going to shift. So therefore, the transition rates and expectation values when an electron is moving between orbitals is going to be non-zero. So that's the non-adiabatic approach in 2 minutes. So next thing, I looked at lead to telluride nanowires, specifically the charge transfer rates. And to do that, I looked at doped lead telluride nanowires. If the lead telluride nanowires weren't doped, they would have negligible charge transfer rates. So by doping these lead telluride nanowires, the charge transfer rate is significantly increased. Now, if you remember from the periodic table, lead has two valence electrons, and telluride needs 2 electrons to fill its outer shell. So lead gives its 2 extra electrons to the telluride. So when we dope these lead telluride nanowires, I looked at lead telluride nanowires doped with sodium and iodine. The sodium atom is going to replace the lead atoms because sodium is giving off 1 electron. It has 1 extra electron in its valence shell. And then it's also doped with iodine because iodine just needs 1 electron to fill its outer shell. All right. So sodium replaces lead, and iodine replaces telluride. And by doping these lead telluride nanowires, the charge transfer rates is significantly increased. All right. All right. Any questions about that? What I just talked about? Okay. So what I did for this was I studied lead telluride nanowires using non-adiabatic dynamics. So what I did first was using VOS software. I used density functional theory to find the energy and position eigenvalues. So if you look at my methods section here, this is the equation I used in VOS density functional theory. All right, and then after I used the VOS output, I fed them into some code I have in MATLAB to calculate my non-adiabatic dynamics. Specifically, I used them to find out how my energy eigenvalues and position eigenvalues changed with time.
What can I?
Sure.
What eigenvalues is not applicable here.
Okay.
Remove them from the text, and I will mark it here. When you are going in your density matrix dynamics category, when you go from the non-adiabatic couplings to equation of motion for rho for density matrix, you are showing some. Can you just point it by laser or by finger?
This one?
Next line. Minus commutator with rho, and the next term here. So it is S, comma, lambda, rho. So this S and lambda likely depend on your non-adiabatic couple,
Okay.
right? Because it's how the lattice vibrations affects electronic degrees of freedom.
All right.
But are there any additional details in equations how the symbol V for non-adiabatic couplings enters into this S and lambda into your equation of motion for electronic degrees of freedom? If you don't have answer right now, let's postpone it. Feel free to look through posters of others and try to borrow ideas from there. But it is a question that a visitor will ask you.
Okay.
Okay, please keep going. Sorry to interrupt you.
All right, so then I used VASP output, and I performed non-adiabatic calculations using my MATLAB software. Specifically, these are the calculations I used. This one, we're finding out how my expectation values are changing with time, and also this equation right here, we're also finding out how the positions of my nuclei are changing with time, because in the non-adiabatic approach, we're assuming that the nucleus vibrates. All right. So then, using non-adiabatic dynamics, I found out how my energy eigenvalues changed with time, and I found out how. No, sorry, I shouldn't use eigenvalues. So I found out how my energy changed with time, and I found out how my position changed with time. All right. Okay. So let's first look at these graphs, my position versus time. I looked at 4 different orbital transitions at different temperatures. You'll see as the temperature increases. For example, I'm looking at the HOMO to LUMO +7 transition. You'll find that as my temperature increases, the charge transfer increases. See this gets wider and wider as the temperature increases. All right. And another thing to notice, if you look at my model here, the charge transfer is localized to my iodine dopant, so it's localized to this region right here. You'll see that on all my graphs. So in summary, two things to know: charge transfer rates is localized in the iodine region, and then as my temperature increases, the charge transfer rates increase. All right. So those are the two main conclusions I drew from my data here. Okay, and then and then these are my energy versus time graphs. I specifically looked at how energy changed with time for different orbital transitions at different temperatures. So I calculated my relaxation rates for my electron and hole. So basically, the relaxation rates for my electron, think of them as the derivatives of these lines here for my energy versus time graphs. My dashed line here is the electron, and my solid line is the hole here. So these graphs are specifically how the energy of the electron and hole changes with time. All right. So I used non-adiabatic dynamics and MATLAB to find this out and to calculate the relaxation rates. And then I used these graphs here to see how my relaxation rates for my electron and my electron hole changed with energy. So if you look at these bottom two temperatures right here, you'll see that they almost have a flat slope. All right. So it seems that the change for these lower temperatures is almost negligible. But however, as we get to these higher temperatures, you'll see an increase, or I should say a decrease in the slope here. All right. So then a conclusion I drew from this is the band gap law, which is this equation right here, the electronic relaxation rates is equal to E to the negative alpha delta E, which is the change in energy. The band gap law is applies for electrons at high temperatures, all right, but not for the electron hole, because as you can see here on this graph, the slopes are almost zero. All right, so that's the conclusion I drew from this. And then the next thing I want to talk about are these graphs right here. I looked at how the electronic relaxation rates increased with temperature. So when I look at these graphs, I essentially concluded that the rate of change with respect to temperature for each orbital transition is essentially constant. It's the same because for both of these graphs, the graphs for different orbital transitions overlap. So therefore, the rate of change with respect to temperature must be the same, no matter what orbital transition you're looking at. So I conclude that that this alpha thing right here, which you see in the band gap law on my abstract, is the same no matter what orbital transition you're looking at, and alpha is 1 over PbTe. Kb is the Boltzmann constant, and then T is the temperature. Let's see, anything else? And then that's it. Thank you.
Okay, good. Thank you.
Any questions?
Oh yes. Anyone wants to ask any question?
How does your observables equations relate to the figure, or one of your figures?
Oh, you mean this?
Mm-hmm.
Okay. So this is the electron relaxation rate of the electron. So this is just the derivative of this dashed line right here. You see all these dashed lines. That's the expectation value for the electron. So this is just the derivative of all these dashed lines here. And then this relaxation rate for the whole, that's the derivative of this solid line here, which is how the expectation value of the electron hole changes with time. So this is the derivative of this graph, essentially. Does that make sense?
The explanation makes sense.
All right.
I guess the notation might be
Oh,
equation might be
these are just typos. I don't know how.
I see the typos, but I mean. So we assume single exponentially, or like only 50 curves. So I guess where does the exponential show up in your observable equation?
Well, you don't see an exponential here because I'm taking the natural log of this relaxation rate. So when I fit this, I would naturally expect it to fit with a straight line. So that's why you don't see an exponential here, because this isn't the relaxation rate. This is the natural log of that relaxation rate.
Right. I guess like the rates that MATLAB, like it's like that code spits out at you. Like those are based off single exponential.
Let me double check that.
No, we will figure it out right now. We cannot wait. Thank you for bringing.
Your call will be disconnected.
That's fine. I do not think anyone is connected from outside. Thank you, Aaron, for bringing this up. So, let's let me bring the. Let's move there. So we do have energy of electron as function of time,
Right.
which equals, if we assume that at time infinity it goes to 0, then it is initial value, and then it relaxes exponentially.
Right.
So if one practices, like divide this by initial value, it will be dimensionless, and then one can practice time derivative. Then it, by taking derivative, the rate will come up front, and it will be exponential. If you take this derivative and then evaluate it at time equals 0, this exponential will become 1, and it will be the rate. So it is one way which is mathematically correct, but in practical implementations, there is a lot of numerical noise if you use grid points. And it is not what the code is doing. Although philosophically, Kevin is correct. Differential way to extract the rate. Now let's do a little exercise. In calculus, we were taught two operations: differentiate and integrate. What happens if you integrate this equation?
From negative infinity to positive infinity,
For the whole trajectory.
it would diverge.
No. Why? If it is just exponential, decreasing exponential, it is not like raising. It's exponential with minus sign.
Oh, this is from 0 to infinity.
Mm-hmm.
So saying what happens if I integrate it? Do you want me to literally solve the integral analytically?
Yes, or you can watch me doing it,
Okay.
or find errors, which I typically do. So if you integrate exponential, you just submerge you change the integration variable, make it k times t,
Okay.
and in order to compensate it, you put constant 1 over k
All
in
right.
front, and then integral of exponential is exponential, right?
Yeah.
And then you put the limits,
Okay.
infinity and 0.
All right.
At infinity, e to the power minus infinity will be 0, right?
Right.
At 0, it will be 1.
All right.
And then the minus and minus 1 compensate. So on the right part, you just practice integration of exponential.
Okay.
On the left part, you have integral of your energy as function of time along the whole trajectory, and you get 1 over k.
All right.
So if you swap it, then you'll get rate of relaxation is 1 divided by integral of energy over the whole trajectory.
Okay.
And it is what implemented in the code. So what you have in your poster is not wrong, but it would be more precise to put this equation. Or keep both of them. Does it address your question?
Mm-hmm.
More questions to Kevin.
How many dopants do you have for those simulations?
How many dopants do I have?
Just count them on your figure.
1, 2, 3, about 4 dopants.
About 4.
Then from the relaxation diagram, it seems just one iodine is involved in the relaxation process.
So can you speak up?
I guess from the relaxation, from the blue figure, it seems just one iodine is involved in the relaxation process.
Right.
What happens with the other one? Why there is no contribution?
Try your best and then I'll contribute.
I'm not sure.
Okay, let me do it. So everything we do here bases it rests on the orbitals, right?
Right.
And these space regions here, it cannot be literally on a dopant. It's same like in the work of Aaron. Even localized polaron is occupies several atomic orbitals in the vicinity. And here, the typical orbitals are in between of these two iodines. So in the space region of the material, which is doped by iodines in general. So it is not localized on a single iodine atom, it is in the vicinity. And it should be interpreted this way. Right now, we are doing a very serious approximation, all of us, which we may decline with years, and it was a plan to decline with years. Right now, initial condition is 1 electronic orbital and 1 hole orbital, which is very comfortable and easy to think about. But generally, if we excite system with certain wavelengths, it creates superposition of several electronic and several hole states. So if you would do this approach, the distribution will be more distributed, more smeared out. And then this artifact of that seemingly localization of one dopant will disappear. So two things. It should be not on the ion but in the vicinity, and second, there could be an artifact of the oversimplified initial conditions. More generally, initial condition should be superposition of several orbitals. Do you buy it? You follow? Agree with me? Okay. More questions to Kevin. Let me ask.
Sure.
So here, your main hypothesis is your specific form of relaxation as function of energy and temperature. And here you show energy offset, and here log, and you see linear dependence, right? Which is fine. And here you are exploring dependence on temperature, which is also great. But you're just literally using the output of Excel, and it is very hard to interpret. Like, what is Y, what is X, and how does the result of your fitting this 4.1 or 4.02 relate to your A capital and alpha lowercase?
Okay.
You need to provide a dictionary somewhere how to interpret what is Y, what is ln X, and how does this number that you get through fitting corresponds to your A capital and alpha. Let me show something. And, so please focus on the other screen. There. Yes. So in the lower panel, you show something like Y equals 4 times logarithm X. And in the abstract, you tell that rate is constant A times exponential minus delta E over Boltzmann T.
All right.
So how to correlate between symbols in this equation and symbols in this equation? Like, what is Y, what is X, what is 4? If you can answer right now, okay. If not, you can think in when you're calm. And
Okay, wait. So I would just divide this by both sides by A, and then to take the natural log of both sides, and then I'd divide both sides.
Kevin, you're probably right, but it is machinery. It is your individual intellectual laboratory. As a user of your intellectual product, audience wants to hear the answer.
Okay.
So, like, definition, what is Y and what is X in here? So likely X is temperature.
Okay.
But let's write it. X equals T, but then, well, it will take a little time to find these correlations. And if I am trying to do this log procedure to your main equation, like here. So logarithm of rate divided by logarithm of your A constant up front will be minus energy offset divided by KT.
Okay.
Right? So 1 over T is a declining function, but minus 1 over T is raising function.
All right.
So maybe.
Hold on, I'm gonna use the bathroom.
Please, please.
So why this is like, it can be fitted with 2 lines. I'm talking about your.
Please, I will try to answer my best, but you may ask Kevin because he will be standing in front of audience.
Are the different data?
Yes. So there are 5 times 4, 20 data points, 20 rates. So 4 rates for each of the value of
different temperatures.
different values of temperature. So there are 5 values of temperature, and for each of them there are 5 data points. They are not much different. They quite coincide. And it looks like he's doing 4 lines to fit the progression of this each of the sequence. Can you please repeat your question so that Kevin will try to answer it himself, and then I will continue my comment.
answer.
Huh? Just formulate a question. We need to help Kevin to train to answer.
Okay, my question was why you are fitting with this exponential type of fitting, not straight line. You can use two straight lines, but
For which one? This one or this one?
lower ones.
Because well, when I look at this, it seems to me that it doesn't really fit a straight line, and that it would fit an exponential more.
I mean, you can fit first 3 points with one straight line and the next points with another straight line. I mean, I'm talking more about the lower left one, but the right one. Then I think you can explain with the energy gap law.
Exactly. You are answering your own question. It is what.
Oh, yeah, that's why I was talking about the straight line.
You understood her question.
No.
She's asking if this data would agree with your original hypothetical law.
I mean, it should, right? Because these points fit an exponential curve.
Okay? I agree with you. But
for first few lines, looks like their relax is pretty faster compared to the next.
the y-axis is logarithmic. Do you see?
I think a couple of them will the gap. If the electron relaxes from higher state, they will relax pretty fast.
Well, it is summary of the data that Kevin obtained. So we can disagree with numerical results, but we cannot change them. So we are doing just fair science and reporting what was computed. Let me continue my comment. So if we take the gap law in this form of negative exponential, right? And then practice the logarithm, like divide k over a, and apply logarithm to left and right. Then there will be logarithm of rate is minus energy offset by temperature.
All right.
And 1 over temperature is a declining function, and minus 1 over temperature is increasing function. So maybe in this, from this point of view, one may try to fit this function as minus 1 over time, or at least explain like why it goes non-linearly.
Okay.
How does it depend on temperature? So it depends like as inverse of the minus inverse of a temperature.
Okay.
If you agree, I'll share the notes. And then if it is correct, then the slope of your of this line is energy offset divided by Boltzmann constant.
Okay.
But please think about it. Try if more equations are needed to explain what is y, what is 4, what is x, and tell if this data are sufficient to to state that then gap law is correct.
All right.
And if it is your fitting, you may also tell what is this r squared and how to correlate this R² constant with the quality of your feeding. Up to this precision, band gap law maintains. Okay. More questions to Kevin? Any suggestions what can be added to his poster? If no, let's thank Kevin once again. So Kevin, please collect feedback and try to carefully read it and implement as possible. So it would be really great if the final versions of posters are ready by midnight tomorrow, Wednesday, so that there will be 2 days for printing. And I will make arrangements so it will be paid and printed on fabric, so it is easier to transport. Anything else to discuss? If no, then well, David, you do not need to do it within 1 day. You can relax and prepare an update for a little longer time. Unless you really want your poster to be presented this year. Then you decline all other activities and rush. There will be no meeting next week. Well, there will be a meeting maybe between Aaron and myself, and Kevin will be still here, but no meeting. And in 2 weeks, there will be with high probability, there will be a guest speaker, the potential experimental collaborator who will share the challenge for where we can contribute our skills to solve real chemistry problem. And in addition to this, upon return from Senegal, the authors who will present themselves will just implement, will probably share the feedback if there will be some interesting. So while presenting, try to make notes or wait right next hour after you finish your presentation, just sit in the hotel room and write down questions and your answers, because it's most valuable part of the conference. For those authors who are not traveling, I will try either to do this task myself, or if Aaron will help me to present, maybe he'll take an heroic effort to do it. And the third option, probably will just take a cell phone and recording mode and record anything that will be spoken about your posters. And after turning back, the idea is that we will use feedback from the posters as an input to convert these presentations into papers, with splitting them as we did in the previous year, chopping on the sections and doing collective editing. Thank you much for your dedication, discussions, and helping each other. Meeting is done, and have a nice 2 weeks. And to those who travel, have a safe